Welcome back to the lecture series in animal cell culture. So, last week if you remember, we talked about the first level, how we can create a system for adult neuronal culture. So, on the week 6, we will continue with that and the different issues, different challenges and what all modern techniques what we can use. And as a matter of fact, this week as well as the next week, we will concentrate on some of these current technologies which are being followed. The idea is here we are taking examples of neuronal cells, because these are the most fastidious one, the most tedious one. But if you can get a hang on these cells, then the basics remains the same. For any other cell type, you really can translate it. That is the whole reason why I am kind of sticking here, because there are several problems what you will be facing while you will be culturing neuronal cells. First problem is their extremely challenging regenerative ability in a culture dish. Even if you can regenerate them, how good neuronal morphology will be regenerated is the second level of challenge. Third level of challenge is these cells have unique connectivities by virtue of which they crosstalk with their surrounding. How you can regain that connectivity? As if you remember, in one of the slides we mentioned that how we can pattern them, followed by, even if you can go this far, you have to ensure that these cells are electrically active. So, how you ensure that these cells are electrically active in the culture? So, there are several problems. So, while we are developing in vitro systems, one has to keep in mind that these factors are being taken into account, so that you get a robust model to explore and emulate the adult or the embryonic or the fetal type of conditions. So, in the last class of the week 5, the 5th lecture if you remember, where we ended was, let us have a recap. So, this is what we were targeting, 3D pattern network of adult hippocampal neurons as a test bed for screening drugs, potential drug candidate against Alzheimer's disease. This is Alzheimer's disease here is a test case, that is it. There is nothing, I mean you can make it Parkinson, in that case your hippocampal neuron culture will become substantia nigra, or you can take an example of say liver cell culture, the disease will change, or you can say pancreatic cell culture, the conditions are going to change. But end of the day, what one has to understand is most of these things are self-assembled pattern 3D structure. The 2-3 things: self-assembled because nature has its own rules of scaffolding and forming a 3-dimensional structure. Second, it is 3-dimensional. Third, it is a 3-dimensional geometry which is dynamic. It grows. If there is an uncontrolled growth, then it is called tumor or cancer, and this 3-dimensional geometry is cross-talking with all its part. So, there is an internal communication channel which is happening irrespective of which cell it is. Further, this 3-dimensional assembly, whichever form it is, whether it is in the brain, whether it is in the pancreas, whether it is in liver, whether it is in lungs, it is interacting with other systems like endothelial system, which is supplying the blood. It is interacting with the nervous system, which is giving its necessary impulse, how to act, how to react. It is interacting with the endocrine system. It is interacting with its own other types in and around. So, in nutshell, what the future, if you ask me that where really all these small bits and pieces of information are taking us and all the studies. And I am going to share, one of you have requested me, I haven't sent that, but I am going to upload them very soon. One of the critical part of all these things that we are trying to rebuild a system in a dish, a small prototype of it, maybe in a 2-dimension and in future in a 3-dimension. So, in a way we should have a miniaturized test bed which carries, mark my word, which carries the minimum signature, bare minimum signature of the whole system. It is like representative signature that, okay, say X cell or X neuron does these things in its whole total context. But here I have a small prototype which can perform these rate limiting bare minimum functions. So, in case of neuron, one such rate limiting bare minimum function is these neuron should be electrically active and should fire. If they fail to fire, then these cultures are of no use. So, in other words, they should be able to do their job of synthesizing electron transmitters and discharging the transmitters, and thereby allowing the electrical impulse to carry from one neuron to the next neuron. And if we could miniaturize it in such a way that it follows a path, apart from it the problem becomes way more complex, and these are the points which I haven't really discussed. Is, say for example, neurons are lying in layers, okay, layer 1, layer 2, layer 3, layer 4. So, it is something like, just let me just add a point that we are into, okay, we are into week 6 and lecture 1, W6 L1. Okay. So, what I wanted to say, so say for example, so these neurons are kind of sitting like this. Let me draw a box to give you that feel, exactly what I am trying to tell you. So, okay. So, this is a 3-dimensional structure, and that is how brain is. This is your x axis, this is your y axis, and this is your height or the z axis. Now, the way they are arranged is something like this. Say for example, in one layer, one neuron. So, this is forming a contact here, this one is forming further a contact here, maybe another layer in the nearby may directly go and form a contact here, another neuron sitting in this vicinity may crisscross and form a contact here. Just look at the complexity. I am just in a small section, I am putting up the complexities. Now, imagine that how really a 3D network will really look like. So, you see that if we try to demarcate them as different layers, say for example, this is layer 1, this is layer 2, this is say layer 3. Okay. So, now we do not have any control when if we talk about a network, that whether layer 1 is interacting with, say, layer 1 is interacting with, in this case, with layer 3, or layer 1 is interacting with layer 2, as well as layer 1 is interacting with both layer 2 and layer 3. So, there are different kind of layering and connectivities which are happening in a three-dimensional network. So, when we talk about a three-dimensional network, it is unlike when we talk about 2D network, where it is very easy. Say for example, I want to make a pattern like this. So, I can make a oval shape pattern like that. We can make a pattern like this, say for example, a squarish pattern will come into these kind of pattern geometries soon. I will provide you, not this week, in the next week I will provide you some of the videos. So, you can make a squarish pattern, you can make a lot of such patterns, and those pattern making is comparatively, mark my word, comparatively easier in a two-dimensional structure as compared to making a something like a 3D pattern. And why these 3D patterns are so very important is that from one layer, how it is cross-talking with another layer is still a tricky problem for us to challenge in an in vitro setup, and these things does matter. Why it does matter? You may have a series of, say, neurons sitting here as a particular neurotransmitter type. You may have another set sitting somewhere out here of another neurotransmitter types, or some mix. So, these kind of interactions eventually determine much of the physiological highlights of the system, and if we really want to understand the physiology of the system, one really has to recreate these models in an in vitro setup. So, keeping some of these basic paradigms in mind, let me pick up where we left in the last class. So, in the last class, if you remember, this is where we were. We have the adult hippocampal dissociated cells, which consists of neurons and the glial cells. Within the neurons, you have the pyramidal cells, you have the interneurons, you have astroglia or astrocytes or oligodendrocytes. Okay. Now, when you have to make a culture, in real life, these cells are all sitting together. So, you have, if you see the network, so network is something like this. So, within this network, now I am introducing. So, if imagine this is the 3D network. Within this network, you will have oligos which are sitting like this, which will be myelinating this. Now, try to understand the complexity here, and then we will talk about how we are going to separate out these cells. These are the oligos. These oligos are involved in the myelination process. So, those of you who are not aware of the myelination process in the nervous system, just to give you a brief idea. So, here you have a classic neuron, and whenever we draw the neurons, we drew it like this. Right. So, you must have seen in the textbook, they have this kind of picture, right. On both sides, as if along the axon, you have a sleeve like structure. This sleeve like structure is what it will be written as myelination, okay, or myelin sheath. And in between, out here, you will see written nodes of Ranvier. On the contrary, so this is a classic neuron which is in the peripheral nervous system. On the contrary, if you see a neuron in the central nervous system, Let me draw, say, if I draw a pyramidal neuron in the central nervous system of hippocampus, which has pyramidal like cell body. Here are the processes, here is the nucleus, here is, let me draw another one that will make more sense to show the myelination pattern. Okay. So, in between, in a cross section, if you ever take a brain slice, cut the brain slice or take the hippocampus, you will see a series of cells which I am now showing in blue. They will be sitting like this. A multipolar cell body is very small. This is, I am kind of drawing it very big. Multipolar cell bodies, and they will be arranged like this. I am just taking example of 2 cells to show you, but this could be way more complex. You are seeing that what it is doing, as if these blue colored cells are forming a similar structure as a very similar kind of covering as you see here. Okay. So, this is a form of myelination what you see in the central nervous system neuron. What is myelination? So, we are aware of the fact that neuronal cells are carrying electrical impulses, right. Now, when they are carrying electrical impulses, just like any other cord which is carrying electrical or anywhere, you always put an insulation across it. Why? Because otherwise if you touch a naked wire, you will get shock, you will get short, because the current will start passing through your body and God forbids it may cause irreparable damage. So, similarly, when the neurons are carrying those current impulses, so they may influence the surrounding neuron which is by its side, so as for them not to influence the surrounding neuron, such that the signal which is being generated, the signal fidelity remains intact and it travels through. These cells have a insulated covering, and that insulation is called myelin sheath. It is a protein secreted by 2 different kind of cells at 2 different places of the body. So, I have to give you this idea, because that way all these words will make sense and you will be able to appreciate that how this whole thing is orchestrated when we talk about a defined system, right. So, what I will do in this class, after giving you this brief idea, because now we are dealing with this oligodendrocyte, astroglia, and then once you know the function of all these things, I will be defining how one can separate them out and how can one reintroduce all these things into the system. So, the first thing what we will be doing, not in this class, in the next class, we will talk about how in real life a cell get myelinated, and how if you have to create a cell culture model, how you can regain it or how you can reintroduce the cell to see whether such myelination happens or not. Okay. Because a neuronal cell without its myelination won't be able to carry over the electrical signal to a long distance. It will be lost because there is no covering on top of it. Okay. And whatsoever model you form will be incomplete without, or inconsequential without, that kind of myelination cover. So, I am closing it here, and in next class we are starting with the myelination problem and the in vitro setup before we really target this adult hippocampal dissociated cell and how to separate them out, because this will slowly take us to the cell separation parameters and how we can really target this problem. Thank you.